Next, let's introduce the coordinate system that we work in to graph two-variable equations, among other things. So this is formally known as the Cartesian coordinate system. You may know it as the graph or x and y axis or something like that. Certainly it, I'm sure, looks familiar to you. So its components, it's essentially two perpendicular intersecting number lines, which we call the axes. So this is the x-axis, and this is the y-axis. And these number lines divide the plane into four regions, which we call quadrants. In particular, the upper right one we call quadrant 1. And then we move counterclockwise around, so quadrant 2, quadrant 3, and quadrant 4. And the point where the number lines meet, this point right here, we call the origin. Now, the key to how this coordinate system works is any point on this coordinate system can be expressed as an ordered pair of coordinates, an x-coordinate and a y-coordinate. So we'll say points on I'll use CCS for Cartesian coordinate system. We'll say it can be expressed as ordered pairs xy, where x is what we call the x-coordinate, and y is the y-coordinate. Okay, so the idea is, again, these axes you could think of as number lines, and if we pick some point, say this point right here, it's going to have some value on the x-axis. Suppose this was x is 1, 2, 3, and then this was x is 4. And it would have some value over on the y-axis. Let's say this was y is 1 and then 2. So we would call this the point 4, 2. It's the point where x is 4, y is 2. The points, our values originate at the origin. So this is where both x and y are 0. So the origin is the point 0, 0. And if we move to the left or down, these would be negative values. So suppose I looked at this point here, where I go to the left 1 and I go down 1. This would be the point -1, -1. So one of the primary uses that we get from this coordinate system is graphing multivariable equations. And depending on the type of equation, there are tricks to getting their graphs. So for example, you probably recall lines. We only need to know 2 points on the line, 2 solutions to the equation, and then we can connect those and get the graph of any linear equation. If we don't know off the bat what a particular equation looks like, what we do is we sketch the graph by just finding some solutions and trying to find a pattern between them. So for example, suppose we wanted to sketch the graph of y equals x squared plus 2x minus 1. Now, presumably you recognize that as a quadratic equation, so its graph should be a parabola. But let's pretend for a minute that we didn't know that. One approach would be to just take a bunch of values for x, find their corresponding values for y, and then use those to find ordered pairs. Now those ordered pairs represent solutions to the equation, and these could be written as points on the coordinate system. I'll find solutions where x is -1, -2, 0, +1, or +2. And these would be found by just plugging those values in for x into the equation. So for example, if x is -2, we'd have y is -2 squared plus 2 times -2 minus 1. So that's 4 minus 4 minus 1, so -1. And when x is -1, we'd have y is -1 squared plus 2 times -1 minus 1. So that's 1 minus 2 minus 1, which is -2. And when when x is 0, this becomes very easy. X squared is 0, 2x is 0, and that leaves us with just -1. When x is +1, we'd have 1 squared plus 2 times 1 minus 1. So that's 1 plus 2 minus 1, so 2. And finally, when x is 2, we have y is 2 squared plus 2 times 2 minus 1. So that's 4 plus 4 minus 1, so 7. Okay, so this gives us 5 different solutions to the equation. And what I'm going to do is just plot those 5 points on the coordinate system and connect them to see what a sketch of this graph looks like. Okay, so the first point we found was -2, -1. That would be located about here. -1, -2, about here. 0, -1, roughly here. 1, 2 is up here, and 2, 7 is, way up here. And we get this curve that, again, we probably are familiar with. This is a parabola. Oops, sorry, that came out super wiggly. Let's get that a little bit better. There we go. Now, again, particular types of equations, linear equations, probably recall, you just need 2 points, and we can connect them to find the line, the graph for that equation. Parabolas, you may know certain methods involving finding the vertex and whether the parabola opens up or down or whatever. But if we just take any random equation, let's say, suppose we wanted the graph of y is equal to 3x times cosine of x or something like that, those approaches, we may not know right off the top of our head what this is going to look like. Now, when you start to study certain types of expressions, so for example trig, one of the things you're going to look at is what does the graph look like, and then you can learn to sketch the graph without just plotting random points. But when you're met with an equation that you don't know what it should look like off the top of your head, then this approach of just picking points, plugging them in, and seeing what you get is a solid place to start. Okay, so I want to derive a couple of particular formulas around the Cartesian coordinate system, one of which being the distance formula. And what I want to know is if I just have 2 random points in the coordinate system. So let's say I give this point coordinates x1 and y1, and I give this point coordinates x2 and y2. How can we find the distance between those 2 points? So if I connect them with this line segment here and call the length of that segment d, how can we find the measure length d? Now the way we're going to do this is by actually picking a third point right here that completes a right triangle with the other 2. And I'm going to give that point coordinates, I'll just call this xy. Yeah, xy is fine. Keep in mind that we have the name of the axes, the x and y axes, but that doesn't necessarily conflict with those values x, y that I'm giving that third point. And the good thing is that x and y there, that's actually equivalent to a couple of the coordinates we already have. Notice that this yellow point here, xy, is actually at the same height as this point here on the left. That is that its y-coordinate is actually the same. So I'll go ahead and fill that in as y1. All right, and notice it's actually at the same position on the x-axis as the top point here. So its x-coordinate, it's actually x2. So that makes this even less ambiguous, between the point and the axes. The coordinates of this point are actually coordinates we already had. Okay, so how does that tell us what the distance here is? Since we formed a right triangle, this thing has got to follow the Pythagorean theorem, right? So this distance here, which I'll call a, this distance here I'll call b, we have that a squared plus b squared has to equal d squared. So I'll write that down here, that d squared has to equal a squared plus b squared. Okay, well, the distance of length a here, the bottom leg of that right triangle, since it's at the same y-coordinate, there is no change in height, there is just a horizontal change, right, from x1 to x2. And whatever that distance is, I can write that as x2 minus x1. So a is equal to x2 minus x1. And remember, a is being squared, so that's x2 minus x1 squared. Now, why that's true, let's throw some numbers in there to convince ourselves that that makes sense. Suppose x2 was maybe 5 and x1 was 1, and I wanted to know what this distance here was. Well, if I want the distance between 5 and 1, I just take the difference, 5 minus 1. Now, of course, we don't want to do that for just 5 and 1. We want to do that no matter what x is, so that's why we have them in there in general as x2 and x1. Now the distance b, that's going to be the same thing, just in the y direction. Since x doesn't change, that distance is just going to be whatever the difference of y2 and y1 is. So we'll call that y2 minus y1 squared. Okay, so that's our distance squared, and if I just take the square root of both sides, we get our distance formula, that d is the square root of x2 minus x1 squared plus y2 minus y1 squared. and that gives us the distance between 2 points on our coordinate system. Another quick formula we can derive very similarly is the midpoint formula. And again, we'll start off with the same idea. We'll take two random points on the coordinate system and give them coordinates x1, y1, and x2, y2. But now I want to look at the midpoint. So basically, if I took the segment that connects those 2 points, I want to take a look at the point in the middle of that segment. And what I want to know is if it's possible to find the coordinates of that midpoint. We're going to use a similar approach here where I'm going to construct a right triangle off the first and off the second sort of half of that line segment. Excuse me. And I'll call these points, let's say A and B. And what we've done here is actually constructed two congruent right triangles. And so because of that, we would know that the distance from, say, this point x1, y1 to the point A is the same as the distance from, say, the midpoint to the point B. And we're going to use that to figure out what the location of that midpoint is. In the midpoint, I'll give coordinates x and y. Okay, so if we look at the coordinates of A, the points A and B here, A is at the same height as our point x1, y1, so it's got a y-coordinate of y, 1, and it's at the same horizontal position as point M. So that means A would have to have, and I'll put these back in yellow, A would have to have coordinates x is x, y is y1. B would have coordinates, so it's at the same height as the midpoint, so it's got coordinate y, and its x coordinates, it's the same horizontal position as x2, y2, so it's got an x coordinate of x2. Okay, now we know, and let's pick a different color here, maybe I'll use green. So the distance here and this distance here have to be the same. Okay, so if we look at what the distance between x1, y1 and the point A is, the y-coordinates are the same, and so it's just the change in the x position. That is, it's x minus x1. And if we look at B, again, the distance between the midpoint and B here, we would have that the y-coordinates are the same, it stays the same height, and it's just the change in x, from x2 to x. So that's going to be x2 minus x. All right, I'll move things around in this equation a bit. We'll take the negative x from the right, add that over to the left. We'll take the negative x1 from the left, add that over to the right. And we'd have x plus x on the left is 2x. And on the right, we'd have x1 plus x2. The x2 that was already there and the x1 that we moved over. If I divide out the 2, we would have that the x-coordinate is x1 plus x2 over 2. Now, I could do all the same tricks I just did here, only using the vertical portions of the triangle, and get a similar expression for y. Y has to be y1 plus y2 over 2. So at the end of the day, our formula for the midpoint between 2 points, x1, y1, and x2, y2, is that the x-coordinate is x1 plus x2 over 2, and the y-coordinate is y1 plus y2 over 2. Essentially, you can take this as just the average of the x positions and the average of the y positions, which should sort of make intuitive sense for the midpoint.